Welcome to this explainer. Today, we are looking at organic chemistry through a totally different lens. Forget the headache-inducing equations for a second. Instead, we're going to treat molecules like a massive social network. We're talking about who's bonding with whom, who's going through a dramatic breakup, and who's completely cutting in on the dance floor. And our absolute VIPs for today, Haloalkanes and Haloarenes. Let's get right into it.
So, picture a standard hydrocarbon chain. Just carbon and hydrogen atoms hanging out in a totally stable, predictable, honestly, kind of boring group. But what happens if you kick out just one of those plain, everyday hydrogens and swap it for a flashy, highly reactive halogen, like a bright chlorine, a heavy bromine, or iodine? Well, it completely changes the entire vibe. The molecule literally goes from being a total wallflower to the absolute life of the chemical party.
All right, Section 1. Meet the halogen replacements.
To understand how these new chemical parties operate, we've got to formally meet our replacements and see exactly where they're hanging out. We basically have two main setups, depending on where the halogen decides to attach. First up, haloalkanes. This is when our halogen grabs onto an sp3 hybridized carbon. Think of this sp3 carbon as your standard, open, single-bond dance floor. Then we have the haloarenes. This is where the halogen attaches to an sp2 hybridized carbon, right on an aromatic ring. Think of the haloarene as a much more exclusive, ring-shaped VIP lounge. And the rules of interaction? Yeah, they change depending on which floor you're on.
Now, what's really cool is how we classify the carbons on that regular dance floor. We sort them by how crowded they are. Imagine the carbon bonded to the halogen is holding hands with its neighbors. If it's holding hands with just one other carbon friend, it's a primary or 1-degree carbon. If it's holding hands with 2 carbon friends, that's a secondary 2-degree carbon. And if it's holding hands with 3 friends, yep, you guessed it, a tertiary 3-degree carbon. As you can imagine, that tertiary carbon is getting pretty packed. Keep this holding hands crowding idea in your back pocket because it's going to be a huge plot point when the reactions start happening later.
Moving on to Section 2, the molecular Velcro effect.
Before we get to the actual reactions, let's look at how these structural differences change the physical, everyday vibe of these molecules, starting with how easily they boil. Take a look at this. Notice how, as you move from the smaller halogens on the left to the larger ones, like iodine, the temperature needed to boil them goes way up. The boiling points of these halogen-swap molecules are significantly higher than the plain hydrocarbons they started as.
So why does this happen? Well, it all comes down to intermolecular forces of attraction, specifically van der Waals forces. But to keep it simple, I just want you to think of these forces as molecular Velcro. As the halogen atom gets physically bigger and heavier, like when we move up to iodine, it has a lot more electrons. This basically turns it into a massive, highly sticky strip of molecular Velcro. A tiny atom like fluorine, that's just a tiny dot of Velcro. Bigger halogens are way stickier, so they cling tightly to their neighbors. And because of that, it takes a ton more heat energy to rip them apart and turn them into a gas. But here's a really fun twist. What if the carbon chain isn't a straight line, but branches out like a tree? Actually, branching decreases the boiling point. Going back to our Velcro analogy, branching is basically like rolling that long strip of Velcro up into a tight ball. Suddenly, there's a lot less surface area touching the neighboring molecules. Less surface area means less stickiness, making it so much easier to pull them apart and boil them.
All right, Section 3, the water click, focusing on solubility.
So we know they stick to themselves pretty well. But what happens if we force them to mingle with something totally different, like water? Well, the short answer is water is extremely clicky. Water molecules are obsessed with each other because they share these super tight, strong hydrogen bonds. When our haloalkanes try to crash the party and dissolve, they just don't have enough energy to break up those strong water-to-water friendships. Since the new attractions they form with water are way weaker than the original bonds, water basically just shuts them out. Because of this, haloalkanes are only very, very slightly soluble in water. Instead, they prefer to hang out in organic solvents, where the molecular friendships are much more on their level.
Okay, Section 4, the molecular partner swap.
All right, now for the main event, the climax of our explainer. What happens when these molecules actually start reacting and swapping partners? We call this nucleophilic substitution. But to understand the swap, you absolutely have to meet the nucleophile. That word literally translates to nucleus-loving. A nucleophile is this electron-rich chemical species that is actively hunting for a positive charge to bond with. In our social network analogy, the nucleophile is the eager new partner, waiting right on the edge of the dance floor, ready to tap the halogen on the shoulder and go, "Hey, may I cut in?"
Section 5. Backdoor versus front door.
So, how does this partner swap actually go down? Well, there isn't just one way. Depending on how crowded the dance floor is, molecules use two totally different strategies. Let's look at the first method, the SN1 reaction. I like to call this the polite waiting or the VIP lounge method. It happens in two slow, distinct steps. Step 1. The halogen partner just decides to leave on its own. It detaches, creating a carbon atom with a positive charge, a carbocation. This carbon just takes a breather. Then, step 2. Now that the spot is completely empty, the new nucleophile calmly steps in and makes a bond. Super polite, right?
Now compare that polite SN1 method to the SN2 method. SN2 is what I call the bumper car backside attack. Here, the new partner does not wait for the halogen to leave. No way. Instead, the nucleophile sneaks up completely from the back and forcefully crashes into the carbon atom. This simultaneous crash forces the old halogen partner to fly right off the front. And because of the sheer force of this backside attack, the entire physical structure of the molecule literally flips inside out, kind of like an umbrella catching a huge gust of wind. In chemistry, we call this inversion of configuration. On the flip side, back in that polite SN1 method, because the carbon was waiting alone in a flat plane, the new partner could attach from the front or the back. That gives us a 50-50 mix of shapes, which is a process known as racemization.
So, which molecule uses which method? Remember our holding hands hierarchy from earlier? Primary carbons are only holding one friend's hand. They are wide open spaces, so they perfectly allow for that forceful SN2 bumper car attack right from the back. But those tertiary carbons, they're holding hands with three huge friends. The space is completely blocked off. The nucleophile literally cannot fit through the crowd to pull off a back attack. Because of that, tertiary halides are forced to use the polite SN1 method. They just have to wait in the VIP lounge for the halogen to leave on its own to make room.
Moving into Section 6, Real-World Halogen Hazards.
We've talked a ton about the abstract molecular mechanics, but why does this actually matter to us? Well, bringing it back down to the real world, these carbon-halogen relationships are literally everywhere. They act as both clinical heroes and environmental villains. On the hero side, we've got chloramphenicol, a chlorine-containing antibiotic that effectively treats typhoid fever. Our own bodies even produce thyroxine, an iodine-containing hormone that prevents goiter. And, in surgery, halothane is used to safely put patients to sleep. But there's definitely a dark side. Dichloromethane is an industrial solvent that can seriously damage the central nervous system. And then there's DDT, the infamous pesticide. The huge problem with these synthetic polyhalogen compounds is that they are incredibly tough. Soil bacteria just don't have the biological tools to break those super strong carbon-halogen bonds. That means they persist in our environment for decades, causing widespread ecological damage.
The chemistry of haloalkanes and haloarenes isn't just some abstract concept trapped in a high school textbook. It dictates the medicines that save us, the anesthetics that numb us, and the pollutants that challenge our environment. It is an entire microscopic social network that completely shapes our macro world. So as we wrap up this explainer, I want to leave you with a thought. Take a look around your house, at your medicines, your nonstick pans, your cleaning supplies. Where else might these hidden, highly reactive halogens be lurking right under your nose? Thanks so much for joining me to figure out this incredible chemical puzzle. Keep learning and keep looking closely at the world around you.